we're going to be looking at proportional reasoning using equivalent ratios. The overall expectation is to solve problems involving proportional reasoning, and our specific expectation is solve problems involving ratios, rates, and directly proportional relationships in various contexts using a variety of methods. In this example, we're using equivalent ratios. Okay, so let's get to our question here. We have a word problem. I'm going to read through it once, and then read through it a second time, highlight important information, and try to come up with a method to solve it, in this case using equivalent ratios. Okay, so the question reads, the table below shows the cost of water for 3 different customers. They each pay the same cost per liter. So here's our table. And it says here that Gabriel pays $46 for water at the same rate, so the same rate of the other 3 customers. Determine the number of liters of water that he purchased. So let's read it a second time and highlight what is important. The table below shows the cost of water for 3 different customers. Okay, and they each pay the same cost per liter. Okay, so that means that the rates that they're paying is the exact same. And our question is asking us if Gabriel pays $46 for water, determine the number of liters. So we have to determine the number of liters of water that he purchased. So we have 3 customers here. So I'm going to organize them. We'll call this customer 1, customer 2, and customer 3. So they all pay the same rate, it looks like. And what we've discovered is that Gabriel, we'll put him in here, Gabe, he pays under the cost $46. So I've kind of extended the table here. What we're trying to figure out is how many liters of water. So we don't know. So we'll use a variable, we'll call it x, to figure out the number of liters of water that Gabriel set up. Now we're going to set up 2 equivalent ratios, okay? And there's a couple ways we could set up these equivalent ratios. Because Gabriel pays the same rate as the 3 customers and they all pay the exact same rate as each, I can choose any of the 3 customers to set my equivalent ratio up with. It might be a good idea to check that the rate is the same. Okay, so we can quickly bring up a calculator just to ensure. Okay, and what we're going to do is we're going to take the amount of water in liters and divide it by the cost each time to see that we get the same number. So 10,000 divided by 9.2. And here's our value, okay? Luckily, because my calculator has lines, I won't have to write it down. I'll see that the number for the next customer, customer 2, will be the same. So let's test it. In yours, you might actually have to write down the numbers so that you can have a comparison between them. If we look, we get the same rate. And then again, boom. So all 3 customers pay the same rate, and Gabriel pays the same rate as them, okay? So what we'll do is we'll set up, like we said, equivalent ratios. And that was just us checking to make sure everybody pays the same rate. So let's say we decide we're going to take customer 1. Okay. Well, customer 1, what we're going to do is, and we're going to set it up his liters over his cost. Okay. So if we have his liters over his cost for customer 1, that's 10,000. Okay. And I'm going to call this row our liters here. Or actually, we'll just denote it with the letter L. Divided by his cost, which is 920. Okay, so on the bottom of our equivalent ratio, we have our money, and we're going to say that that is equal to, for Gabriel, his liters are unknown, right? We have that letter X to represent the unknown variable here. We don't know how many liters he purchased, but we do know he paid $46. So here's one of the equivalent ratios we could have set up in this case. I'm going to take this and just move it to the bottom of the page, and I'll know that you can't quite do that on yours. I'm going to move it because I want to show you that there's another set of equivalent ratios we could have set up. So if you notice, I kind of organized the columns, that's vertically, by the person, customer 1 and Gabriel, we'll say. I could have also organized it possibly by, let's say, well, I guess we'll do liters, blue. We could have done liters and money, and had actually the 2 names, maybe customer 1 and Gabriel, as our roles. So customer 1's liters were 10,000, we knew that, divided by Gabriel's liters. Well, Gabriel's liters is our value of X here, that's our unknown, is equal to, what were the money? or what was the amount that they spent. Customer 1 spent $9.20 divided by what Gabriel spent, which was $46. Okay, so I'm also going to take this. We're going to do kind of a side-by-side comparison as we solve them. So if you've noticed, I've set up two sets of equivalent ratios. Both of them we're trying to isolate for the variable x. Okay, so what we'll do in the first one is I'll solve the one on the left. We'll call this number 1 and this number 2. We'll solve the one on the left for x, and then from there we'll solve the one on the right for x to see if we get the same values. Because they're equivalent ratios, or in this case you could also refer to them as fractions, what we can do to simplify them to get rid of the actual fractions is we can cross multiply because they're equivalent. So I'll take the 920 times x and the 46 times 10,000. Okay. So on the left side, the equal side still stays down here in the middle. We have 10,000 times 46 will actually equal 460,000 is equal to 920 times x. So we'll say 9.20 x. Right? When we have a variable and a coefficient beside each other, the operation between is multiplication. From there, remember our goal is to still isolate for x. So what we need to do is divide both sides by 920. Okay. So when you divide the right side by 920, we're reducing the number to 1. Now, a lot of people refer to this as canceling. But what's actually happening is if we take 920 and divide it by 920, think of it like dividing the number, maybe write it on the side here, writing the numbers 2 divided by 2, well, that's just 1. 920 divided by 920 is 1, so we're left with 1x, okay? And 1 times x, just like 1 times any number, say we had 1 times 5, is just the number itself, 5. So in this case, 1 times x is really just the number x. So I'll bring it down one more step. There's really not much to simplify there. On the other side, though, we do have to divide. So let's take that 460,000 and divide by 9.2. And it turns out it gets 50,000. Okay, so 50,000. Remember, x was representing the number of liters. I'm writing it again here, right? Because remember, I simplified 1x to x. 50,000 liters is the amount of water that Gabriel purchased. Okay, so we solved that in our first set of equivalent ratios. Let's do the same thing in our second. And you're going to notice a relationship right after the first step. Because they're equivalent ratios, we're going to cross multiply to do some simplification. When I take 46 times 10,000, well, that's really similar to what we did over here. Remember, the first step is to bring down our equal sign. Our equal sign still stays in the middle. 46 times the 10,000, that's 460,000. And x times 920, which is the same thing we did over here, we get 9.2 or 9.20x. Okay? And we know that this and this are now the exact same. We're at the same point where we've now set up our equivalent ratios and we're doing the same operations from here on out. So like we said before, we're going to divide both sides by 920 or 9.2. Okay. That'll leave us with just x on the right side and 50,000 on the left. So in the end, it turns out that Gabriel purchased 50,000 liters of water for that $46 that he spent. Okay. If you'd like to know other methods to solve this question, look at our other playlists for different ways to get to the same answer.